that will help you to write the report. Okay, so you should write the report and send it to me within next week, within next Thursday. Then in the report you will write the circuit diagram, objective, then you have no need to copy the apparatus used because apparatus used will copy from here. Then you write the whatever is asked in the report. Okay, I shall discuss that one. Still, you follow the report, what is asked to write in the report, you write that one only. So objective of this experiment is to study the role of series voltage injection in power transfer. You have already learned the study of power transfer in your third year second sem lab. Anyway, it was in online mode, so I do not know how much you have understood. But from theoretically, you know that when there is a transmission line, then power transfer from one end to another is depend on magnitude of voltage as well as angle difference between them. And active power transfer is mainly depend on the angle difference, phase difference between the voltages. And reactive power transfer mainly depend on the difference in magnitude of voltage in between two uh, ends. So here that we know that we performed one experiment also in case in our third year second sem lab, or we have learned this one in power circle diagram, theoretical part of in power circle diagram thoroughly. But here now we shall add some extra uh, facility to the line so that power transfer may be improved. What extra facility, what extra support? That we shall provide series voltage injection. So some voltage will be injected in series in the line, and we shall observe how the power flow is changing, and between in the line, and as well as if there be two line, then how power flow can be controlled between two lines, that we shall observe in this experiment. So actually the first objective is the study of power transfer uh, in presence of series voltage source. So this in this figure, if you see, actually this is a single end transmission line. Actually this is one end, this is one end. Now here in the both end there is low source, but you have learned there is one in one end there is a source and another end there is a load. But this type of situation may also arise. Actually this is a generalized representation, because power may flow from sending end to receiving end as well as receiving end to sending end, depending on the magnitude of voltage and the angle difference between them. Anyway, then in the line there is line reactance. Then the power transfer is actually V1 V2 by X sine delta. Here it is assumed that VR and VS both are equal to V. Okay, so that's why VR V2 by V1 V2 by X sine delta, in the numerator it becomes V square, right? Now if there is a reactance, then V1 V2 by V square by X sine delta must be the power transfer. Now if we want to change the power transfer, then we can improve the voltage, and otherwise we can reduce this X that we have learned in our when we learned compensation. Now this X we can reduce by inserting some capacitor in series with the line, that may be Xc. So that is done here. So effectively power transfer become V square by X minus Xc sine delta. Okay, I am removing all this. So it is V square by X minus Xc sine delta. So actually what is happening? This capacitive voltage drop is compensating inductive voltage drop. So effective voltage drop is decreasing. That's why actually the effective reactance is decreasing. So we can improve the maximum power transfer through the line, or power transfer through the line at any angle. So, but the problem of capacitor is there may be resonance, series resonance, and that may lead to Ohm's condition in the system. So that may be overcome using series voltage injection. Instead of capacitor, if we provide this series voltage, okay, which is controllable, power electronics control is there, or say assume it is controllable, and that voltage may be added in phase with the Vx. Vx means the voltage drop across the line reactance, or out of phase with the Vx. So if it is Vx and you are adding a voltage in phase with the Vx, say Vc, then what actually you are doing? You are actually increasing the voltage drop through the line. So you are actually increasing the reactance of the line, inductive reactance of the line. So that will not help in the in improvement in power transfer. On the contrary, if you add this Vc in opposite direction to Vx, then only the effective voltage drop in the line may be reduced. In that case, we can get this type of phenomena that power transfer to the line will be increased. But in this case, we have not included any capacitor, but we have included a voltage source. So that is controllable voltage source. So actually, there is no question of series resonance. Okay, so that may be avoided. Now this voltage source, if we give this VQ, if we give from any power electronics control circuit, control device, then if this voltage may be added at any angle. Here I have shown that it has added at in phase or at 180-degree out of phase with the series voltage drop. But it may be added in at any angle if we control it through converters. But that is not I am not discussing that one right now. So now return back to here. So actually this is the Vx. So maximum uh, reactance drop in the line is Vx max A. That means there is no compensation. Obviously, then if we use the compensation minus Vq, then you can reduce it. Okay, so in that way you can reduce it. Now in that way you can go up to this and you can add, you can make it Vx minimum. Otherwise at that point you can increase it also as plus Vq. So actually I want to say that here if there this is the voltage drop in the reactor, then you can add Vc in 180-degree out of phase or in phase. Okay, so generally we adopt in phase 180-degree out of phase injection, so that there will be an improvement in voltage. Then what is actually happening? We are increasing, giving this voltage at 180-degree out of phase. That means actually whatever voltage is available here, say Vx, that is actually improving when it is coming to receiving end. So as if some voltage is injected in the line. So there is a rise in voltage as well as improvement in phase angle, load angle actually. So there will be an improvement in power transfer. So in laboratory, we have not used any control power electronics controlled voltage source. Instead of that, we have used a secondary of a transformer. Say in this voltage source, we may use in this way also. This may be secondary winding of a transformer. It may happen, and the primary winding is connected to some other source. It may happen. Then also controlling the primary winding, you can control the voltage injection. That actually we have done in our laboratory. Okay, in that way we have simulated series voltage injection in the laboratory setup, and we have studied what is the effect in power transfer. Now, what is the objective 2? Now, in objective 1, I hope you have understood that. So, by controlling the series voltage injection, we can control the power transfer through it. So, what is actually happening here? Actually, here, if we use the capacitor in the first figure, actually we are injecting some Xc, that is reducing the X of the line. But in the second figure, actually we are including some VQ or series voltage injection. So VQ by I actually as the compensation of the inductive reactance. So in that way, we are improving the power transfer through the line. So in short, power transfer through a line, it may be controlled by series voltage injection, right? If you have any doubt, you must interrupt me and ask. Then next objective is to study the role of series voltage source in power transfer between two lines. Now say if there be two line in parallel or maybe interconnected through some interconnected power system, then there may be the provision of series voltage injection. Now series voltage injection can be given using static synchronous series compensator. That is no need to know for you. Anyway, this can be given, that control voltage may be given using static synchronous series compensator. So actually that facility to provide the series voltage injection. So by controlling the series voltage injection, actually we can control the effective reactance of these two lines. So we can actually control the what will be power transfer between two lines, or say control the power transfer in the interconnected lines, right? So this is our objective 2. Now this is the circuit diagram. Circuit diagram, you see if you have can remember your power transfer experiment, then actually there was a transmission line, uh, and transmission line was represented by an inductor. And we have learned the study of power transfer through it. So there was voltmeter at the receiving end, sending end as well as receiving end, and we can control the phase angle through it. Delta we can control and can study the power transfer. This is the same experiment. So this terminal actually 1, this terminal actually 3 here. So there was an inductor in the line. So that one inductor is taken to simulate the line. Simulate means as if you are creating the behavior of the transmission system or any system in laboratory or in computer. So this is actually experimental simulation. When we write anything in programming, then we make that computer simulation. So is it justified to represent a line by an inductor, because actually line it has a distributed parameters. But actually when we consider lossless transmission line, if it is a distributed parameters, we can simply represent it by its inductance only. With that logic, we have represent the line in this way. Now we have to apply some. So this is the line, say line impedance. Then we have to inject series voltage injection. Then we have to send the set some receiving end and sending end. So this is the one end and 2 is another end. Now since the series voltage injection in our lab is given through a transformer, so that transformer primary must be connected to some other source, right? So actually this is the case. This is the laboratory setup. And if we want to control what will be the series voltage and what will be the angle of it, say sigma, then there must be a phase shifter which will control the voltage load angle in between this. At the same time, if we want to control the angle between sending end and receiving end, finally, say in between 1 and 2, if you want to control angle between them, say delta 1, 2, then you need phase shifter, because in lab there is no generators, no prime mover. Then how you can control phase angle, load angle? Because in practical power system, when there is a load, that create the loading of the generator, and when we supply the prime mover input, from there load angle is created. Okay, so in that way power transfer takes place. But there is no provision of that in laboratory, so we have to simulate all these things. That's why phase shifter is required. I hope you have understood. So let us come back to circuit diagram. Then obviously this is the line and this is the series voltage injection, right? So it is, some terminal is marked as 1, 2, 3 and 4 is the, so see, if it is series voltage injection, then 4 is the primary side of that transformer, 5 is the secondary side of that transformer. So that means 4 is injecting power to 5, right? So how we can sanguine for a transformer that power is transferred from the 4 to 5? Because in this case transformer secondary is also energized with the line, because in line at the end 1 and 2 there are voltages. So how we can get it sure? So for that reason, when we start the experiment, we must ensure P4 greater than P5. It is written in your instruction manual, you can say. P4 greater than P5 means 4 side is primary, is not it? Because input power will always be more than output power. there will be some loss in input side. But here it is that in this experiment there is no such high load in the transformer or in the transmission line. So actually there will be very small difference in between P4 and P5, but there is a noticeable difference, but it is not huge as it will be in practical power system. Now, if we want to control the power transfer in the line, say in between sending end and receiving end, in presence of series voltage injection or in absence of series voltage injection, then we must control the angle between these two lines. So that is delta 1 2, right? So that delta 1 2 is controlled using phase shifter 1, right? Actually, same from the same power supply, one voltage is given at the end 1, and same voltage is given through a phase shifter to the end 2, so that we can get this angle difference. Similarly, if we want to control the angle difference between this angle of voltage injected at 4, then obviously whatever power supply voltage is available, we must shift that. We must that angle we must shift. That's why we need another phase shifter in the injection part, right? So as if we can consider this one, the main line, as the line 1, and as if the transformer's primary part as a second line as line 2. So when we are studying the study of power transfer, then we are assuming in study of power transfer using series voltage injection, then we must make L1 P4 greater than P5, so that it can be ensured that some voltage is injected on the primary side. Otherwise, if P5 greater than P4, actually that will be the primary side. So there is no injection. Actually, in that case, that is working as a source. It is taking power voltage from the line. Okay. So then the simulation will be wrong. In the second run, when we shall learn, we shall observe what is the power transfer between the line, then we shall see that what is happening when through this transformer power is going from the line to the transformer, or the in the transformer, previously transformer primary. How we can ensure that? Then for second run, P5 should be more than P4, because in that case line should be primary, line side should be primary. So in this way we can simulate the two conditions of one is study of power transfer through line, another is study of power transfer in between two lines in presence of series voltage injection. So what is the setup? Transmission line I have discussed, it is represented by a reactor. Series voltage source is represented by 1:1 ratio transformer, so that if you can measure the voltage here, same voltage will be available here. So only 1 voltmeter will be sufficient. Single phase variacs to control the voltage magnitude, because when we shall study the uh, facility of series voltage injection, we must make the sending in and receiving end voltage and all voltages at constant, so that they should not affect the power transfer. Next is three phase variac is required for the phase angle control. Okay. So actually this phase shifter 1 is required to control voltage in two ends of the main line, and there is another phase shift which control the magnitude and angle of the uh, injected series voltage. Okay. So this is three phase variac, actually phase shifter. This is one thing, because phase shifter is actually given through a three phase transformer. So these two will be combined. Now, which type of measurement is required? So we need to measure the voltage at every point. So using one voltmeter, we can measure the voltage 1, 2, 3. So 3 voltmeter will be there. At the same time, on the primary side of this transformer, that is at V4, we should measure. Okay. Now you must remember here V1, V2, V3 are voltage with respect to a reference, but V4 is the voltage, V5 actually voltage between 3 and 2. So in case of, we shall put the voltmeter terminal in between these two, right? Meters, all these voltmeter required. Here it is written two ammeter, ammeter to measure the current, ammeter to measure the primary current of series injection transformer. But this facility is not right now available, so there is only one ammeter in the line. Then wattmeter is required to measure power at every point. At the same time, wattmeter is required to measure power at the primary side of the transformer. You must remember same current is flowing through the through point 1, 2, 3. So we can use same parameter, same wattmeter, only changing the voltage terminal we can measure the power. But for P4 and P5, we have to set another 2 voltmeter, 2 wattmeter, because for 5, 4 the current is different, and if we want to measure P5, then voltage is different. Voltage is in between 2 and 3. So actually 3 wattmeters are required. Now this actually the figures of the photos of phase shifter. So actually there are knob. Using those we can adjust the angle 0 degree, 120 degree, 180 degree. So actually it controls the angle between the phases from primary to secondary within the transformer. According to that, phase angle in the experiment gets changed, but it does not change to 180 degree. It changes within the 40 to 45 degree based on this. Actually, here there is no much control in phase angle or load angle in the laboratory, because you know, in case of actual power system, if you simulate this same system in actual power system, then what will happen? These systems are not connected. They will be totally different. So here actually see this terminal 1, terminal 2, terminal 4. Actually we are given all from the CAC supply, and we want to make the phase angle difference using phase shifter. So same source, but if you use a practical power system, then in the terminal 1, terminal 2 and terminal 4, there will be entirely different generator. So their characteristics will be different, their voltage, magnitude and angle will be individually controlled. So their control range will be more. But if you perform this experiment in the laboratory, you will see you will not get so much control. A number of reading will not be available. We can hardly get one set of reading, but that is not at the same point. Every day it will be changed, because every day the generation to voltage from the CSN change to some extent, and obviously it will be dependent on the at the time where you are, at which point you are performing the experiment. Okay, because when all the load in the in the system, so then a V, actually whatever you are using, actually it has an inherent phase angle, so inherent load angle, that also affect the experiment. So apparatus used, whatever I have discussed, that is written in short. Now here actually 3 phase angle meters are used to measure delta 1 2, delta 1 3, delta 2 3. What are these? Actually, delta 1 2 means angle difference between in between voltage V at the node V1 and 2. Delta 2 3 means in between 2 and 3. 1 3 means in between 1 and 3, in that way. So there is a phase angle meter. Why phase angle meter is required? Because from the angle only you can see, you can pretend that in which direction power is flowing. So this is the actual setup, right? So this is the actual setup. Here you see these boxes are actually phase angle meters. Okay, it is showing 23.4, 13.5, 12.05, anything. And here is some LED is glowing. You may notice I am giving the arrow. This LED actually indicating lead or lag. There are two LEDs corresponds to lead or lag. From there you can we can identify whether the voltage is lagging or leading. But with respect to what? Actually, in this phase shifter, there are two set of inputs. One is input, another is reference. So actually, if input you are giving V1 and in reference you are giving V2, that means you are measuring voltage phase angle of V1 with respect to V2 in that way. So if it is showing 13.16 degree leading, that means V1 is leading from V2 by 13.16 degree. That is the thing. And these all are voltmeter. One is ammeter, this is the ammeter, and this is the voltmeter. But generally we use voltmeter from the analog voltmeter with two wires. Now, so these are actually this thing actually connected in the system, because these are so complicated. If we want to connect it in every lab, it is not possible. So generally it remain connected, but we have to identify what are the phase shifter input and what will be the reference. That means what is actually the phase shifter measuring, that we have to ensure. For that reason, in your instruction sheet, you will also see it is written, note the connection at the reference and input terminals of the phase angle meter and note down the following table. Why is it is required? Because you must not be sanguine about this, because in every case the power transfer will be dependent on that. So you must check this one before starting the experiment. So there is a table in the phase angle meter connection there in your laboratory instructions book. It is there. Now, if we see the partial setup of the laboratory, it is like this. So actually, these are the phase shifters, okay, and this is the actual. This is a three-phase variac. From there, you can vary the voltage. So this is the transformer side, transformer symbol you can see, and this is the line. Okay. Shall I repeat? Let's show one, see one time. These are the phase shifters. This is three-phase variac. This is the transformer, and this is the line. And all three variacs, all these phase shifter you can see. So from there, delta 1, 2, if we are measuring delta 1, 2, that means voltage of angle of voltage V1 with respect to 2. So V2 should be reference, V1 should be input. Delta 1, 2, V1 should be input, V3 should be reference. So in this way we can tabulate it. Actually in lab we shall check it. Now run 1. What is given in run 1? Adjust the variacs at the two ends of the line to make V1 equal to V2. So actually we shall adjust the three-phase variac so that at one end the voltage at V1 and V2 will be same. Adjust the phase shifter such that V2 leads V1 by a suitable angle. It is not mentioned because it is very difficult to set a particular angle. So it is not mentioned. You just make V2 leads by V1. So what will happen if the voltage V2 is leading from V1? That means power is transferred in this direction, because voltage magnitudes are same on both sides. Adjust the variac and phase shifter, variac 2 and phase shifter, such that P4 greater than P5. That means you ensure the voltage injection, right? So this is the thing. Then what we have to do? We have to take the reading of different voltage at different nodes and power at different points. Now you see here, say power is flowing in this direction. So if we consider at this for this series voltage injection, so from the point node 2, power is flowing towards the 1, because the delta 1, 2 is set in this way. Again, the P4 is set greater than P5. So some power will be injected through this through this transformer. So what will be the available power at P3? P3 is going in this direction. When P3 will be going in this direction, when 3-1 is again leading. Anyway, so what we can see there at P3, at the point node 3, total power received will be P2 plus P5, because P2 some power was sent to the receiving end and some power is injected from some other source, through some line. So actually power balance equation should be P2 plus P5 equal to P3. At the same time, what will be the voltage at V3? V3 voltage should be V2 plus V5. If the voltage are additive, if there be voltage is injected, right? So in that way, we can verify this thing from the phasor diagram that you will draw in the report. Then next is the run 2. Run 2 is the same, only the reversal of power flow. So here voltages are kept fixed, but phase shifter is adjusted in such way that V1 leads by V2. V1 leads by V2 means now power is flowing in this direction. And it is again maintained P4 greater than P5. So voltage is injected, power is injected. So what is happening? At P2, power is going towards the 2, and P5 is injecting, and from P3 at the point 3 power is incoming. So what is the net power obtained at node 2? P3 plus P5. Okay. On the condition then when power is flowing in this direction, right? So power balance equation should be P3 plus P5 equal to P2. Now then what will you do? We do in our experiment? We shall read this power, note this power reading and verify whether P3 plus P5 equal to P2 in run 1 or not. In this way for run 2 or not. In this way for run 1, P2 plus P5 should be equal to P3. But it is not mandatory that P2, P3 plus P5 should be P3. It should have condition that all the power is flowing in same direction. Otherwise, it may change also. So in this case also, V3 plus V5 will be equal to V2. Now next is the run 3. In run 3, it is very difficult to reach this condition. So no condition is given. Only condition is given you make P5 greater than P4, so that we can ensure that power is flowing from 5 to 4, right? So actually, if P5 greater than P4, the P2 is the receiving end. So towards 2 power is going, P5 is going out, and P3 is going. Sorry, that is not there. So actually only one condition is given, power should go from the line to the transformer, right? Now if we see that receiving end is 2, then towards 2 power will flow, from 3 power will come. So from power, some power is going out. So what will be the power available at the point 2, P3 minus P5? So because some power has gone to some other line. Now another condition may be there, that is powering is flowing in opposite direction, because that is not mentioned that whether delta 1 2 will be lag or delta 1 2 will be lead. So power may flow from 1 to 2 or 2 to 1. So for two different conditions, the power balance equation will be different. So for the second condition, when power is flowing from 2 to 1, then obviously the power received at 3 is P2 minus P5. So in this case, P2 minus P5 will be P3. So this is seen when we perform the experiment in lab. Sometimes the second condition is achieved, sometimes the third condition is achieved. Sometimes it may happen that this condition is not possible to achieve. Generally, it is observed when there is the machines are on in the machine laboratory. It is we observed. We could not find the reason very positively. Anyway, so this is the thing. That's why the angle is not mentioned properly. Only it is required to control to make P5 greater than P4, so that we can ensure some power is going from the line to somewhere else, here in the transformer side or in the second line. So why it is written that it is the power transfer between the lines? Because here power is transformed from here to here. Okay. And here, what is the difference? Then the first run 1 and run 2 is also power transfer between the lines, because but in the run 3 we have not injected any voltage in the transformer. But when in run 2 and run 1, if you see run 2 and run 1, then there is a, we are observing there is a injection in the line along with the line reactance. So this is the study of power transfer in presence of series voltage injection, and run 3 is the power transfer between the lines. Okay, here in that case this transformer is helping to power transfer from line 1 to line 2. Now, say performing the experiment in laboratory. If we perform the experiment in laboratory, at first we have to adjust the V1 equal to V2. So that we can do in this way. So this V1 minus V1 equal to V2 is very tricky. We generally set both end voltage as 50 volt, and we adjust the variac in that way. Okay. So that both receiving end and sending end voltage is set to the 50 volt, right? So this is the adjustment of voltage on both sides, so that all the power transfer takes place only for delta control. Next is adjustment of phase shift. So for adjustment of phase shift, we have to control the phase shifters, these two phase shifters, to adjust the phase shift. This is another phase shifter, three-phase barrier. Using these three, actually we reach the desired phase shift. We have, because we have to reach two conditions. One is power transform from 1 to 2 or 2 to 3, and we have to reach one for run 1 and run 2. P4 is greater than P5, and for run 3, P5 is greater than P4. So this adjustment we have to do using the phase, controlling the phase shifters. Then for tabulation, we have to read the tables in this way, read the meters in this way. Okay, only read the meters, 3 meters. So experimental results, if we tabulate, you will get this type of result. All the powers we must measure at every point, voltage at every node, and load angles, and current, series current in the line. Line means in the line where series voltage is injected, not in the transformer. Now let us analyze the result one by one. In case of your report, you have to analyze the same result, same data. This PPT I shall give, and whatever is written here I shall give you. You write the table only once, not this separate table is required. Then you write the verification of result of run 1. Then you justify your result as I am discussing right now. Along with that, you must draw the phasor diagram. All of you have understood what to write in report? Can you hear me?
Yes.
All of you, have you understood that what to write in report?
Yes, ma'am.
There should not be any confusion regarding reports. So this is the result. Okay. So since you have not written in your hand, so it is very difficult to see it and decide it at a glance. Let us take it one by one. So you know, if you see the analysis, then power balance equation should be P2 plus P5 equal to P3 for run 1. Just extract P2 and P5 from here. P2 is 19.2, P5 is 8.2, right? And P3 is 27.2. Then when you add P2 plus P5, then check whether P2 plus P5 is approximately equal to P3 or not. Here I have not added. You add it and find the difference, deviation, and write your justification. Understood? If anybody do not understood, then ask me. Along with that, you see all the voltages are given. Their relative angles are given. So obviously you can draw the phasor diagram. Some phasor diagram is given, but it is not 100% correct. Firstly, here current is there. What is current actually? If you see current, current is flowing through the line. For current, there is no phase angle meter. But this line, this is creating voltage drop V13. So wherever the V13, What will be the current and phase of current with that? 90-degree lagging from there, is not it? Because V13 is JIX. Understood or not?
Yes, ma'am.
So in this way, you have to draw the current phasor also. That is not present here in the phasor diagram I am showing, because I have copied it from some laboratory report. But you must show that one because I am explaining you. So what you can do, draw, say just if you draw the phasor diagram by your own, if it is V1, then delta 1 to lag. That means who is lagging? V1. Then V2 must be somewhere here. If you draw in proper scale, you must get it. Then delta 13 lag 42.2. Delta 13 V3. V3 is some 75 and it is lag. So that means it will be 42.2 and this angle is 22. Then this angle you can verify. You must verify this should be near to 16.5. You can see this is lead, and in the phasor diagram you are also getting lead. But how much lead you calculate from the phasor diagram? This is one thing. And it is P5 is given there. Okay. So here power, in which direction power is flowing? In this direction. So V3 should be V2 plus V5. So here V3 should be V2 plus V5. So this should be V5. And V13, if this is the V13, so phase of I should be 90-degree with that. So this will be the phase of I. So in parallel to that, you draw a line from the origin. Then you can get the I and draw it in proper scale. Have you understood or not? Because you have to draw it yourself. If you do not ask us anything, then I shall pretend that you have understood. So this is the thing. You must do it yourself, because whatever phasor diagram I am showing, all of your seniors have not done the right thing. So you must do it yourself as I am explaining. Similarly, for run 2, the power balance equation should be P3 plus P5 equal to P2. You must justify why it should be, and from there you verify it from your reading. So if you think you will forget, then you write that for in report for run 1 and run for every run, write the verify the power balance equation with proper justification. Report, verify the power balance equation with proper justification. Draw phasor diagram including all voltages and current except V4. V4 you cannot include because V4 is the other side. It is not in the same system. It is in the other system. Similarly, for run 3, you see for run 3, what we have got, delta 1 to lag and delta 3 to lag. So delta 1 to lag, delta 3 to lag. So delta 1 to lag, delta 3 to lag means 1 minute. Delta 1 to lag means power is flowing in this direction, right? And delta 3 to lag. So power will be flowing in this 1 minute. I have told you for run 3, there is a specific condition. I do not know. We do not know before running the experiment which situation will be achieved. So here we have achieved for delta 1 to lag and delta 3 to lag. What is the meaning of delta 1 to lag? Power is flowing from 2 to 1. So this in this direction, and 3 to lag means in the same direction. So this one. Now power is outgoing. So what will be the equation? P2 minus P5 equal to P3. The second equation will be valid here, right? So in this way, you can write P3 minus P5. 1 minute. Delta 1 to lag or lead. 1 minute. No, I was correct actually. It was 1 minute. Let me clear it. It will be the opposite direction. I was correct. Just modify it. You see here delta 1 to lag, delta 1 3 lead. That's why 1 2 from 1 to 2 power is flowing in this direction towards from 2 to 1, but delta 1 3 is lead. So power is in opposite direction. So actually here delta P3 will be received but in opposite sense. So here actually at P2, P3 minus P5 should be equal to P2. So in that way we have to justify. Whenever you have run it for the first run, so you can see here, for the first run you have got both this connection lag, but here we have not achieved that condition. One is lag, another is lead. So that we have to verify considering the equation. But here you, since current power is flowing, power will show the opposite direction, but this direction will not be identified by the both wattmeter. We shall change the polarity and we shall measure the power, so we can only understand the magnitude of the power. So in that way, we shall get P3 minus P5 equal to P2. Because delta 1 3 lag means P2 should receive the power. So, sorry. So P2 should receive the power. Delta 1 to lag is showing that it is in this direction, but delta 1 3 lag. So P3 will inject the power. Some power will be outgoing. So P2 should receive, but that will not be observable from our setup. We shall see as per justification direction in this. But if you calculate the power, you will show only the magnitude, and you will get this equation to be verified. So in the same way, you justify your result. In the same way, you draw the phasor diagram. When you draw the phasor diagram, you will see in this case V5 is added in, for this particular case, V5 is added in the opposite direction. Okay. In other cases, V5 was added in the positive direction, or more less than angle 90 degree. Here it is angle is 125 degree. So that you draw your by yourself, and in every case you must draw the phase of current, right? Now why we have learned this one, what is the actually practical application of this? That so using the series voltage injection, we can control the power transfer through a line, okay, or within the line or between two lines. But actually it is a small replica of unified power flow controller. What is that? Unified power flow controller is a fax device where we use two converters back to back. One which take the supply voltage from the supply side, then second set of converter control it according to supply, inject some series voltage in series with the line at any angle. Now VPQ may be added at any angle, say sigma, using this converter control. That is the UPFC. So actually if this is the voltage V, then VPQ may be added at any angle 0 to 360 degree. So now what will be the effective voltage? Effective voltage, the locus of the tip of the effective voltage will move on this circle, right? Now using this UPFC, we can control voltage, line impedance as well as phase shift. Voltage regulation means voltage drop regulation. Line impedance control means series recompensation. Phase shift means controlling of the power transfer. Because if you can control the load angle between the two voltages, then you can control the power transfer easily. So actually This is the thing. So voltage can be added at every point. Now here obviously phase angle of series injection may vary from 0 to 2 pi. At any angle you may add, and magnitude may vary 0 to VPQ max. This VPQ is a voltage, but that voltage is controllable using the series converter side. So that may be 0 to maximum value depending on the converter configuration. And here converter 1 provides active power from sending end bus and a converter 2 exchange it with the line. So when we use it for voltage regulation, then obviously we add the voltage in series with the line. So obviously voltage will be improved, effective voltage will be improved, so it will improve the voltage regulation. If we want to make line compensation, so if this is the voltage, if this is the voltage, center one, then I has at an angle of phi, say with it, then this should be JIX. That means uh, phase of voltage drop in the line. So actually this is the V drop. Now if we add in phase with the V drop, then we can increase the line impedance. If we add in the out of phase of with the V drop, then we can compensate the line impedance. So in that way, it can use as line impedance compensation or series compensation, both in inductive side and capacitive side, but we use it for the capacitive side. So next is, say voltage is this one, the central one, right? This one is the voltage. So any voltage. So if you add it with this, some voltage, then what will happen? Say this is the reference. I have drawn, say, with 90 degree, for example. Then actually the effective voltage will be to some angle, it will be the leading angle will be reduced with the reference. Now it in advance with that. Then the angle will be increased, right? Both plus sigma or minus sigma. In that way, the phase shifting can also be controlled, right? In that way, using the series voltage injection, say you have learned that critical load angle, maximum load angle we must provide for a Pmax. Then what will be that? That can be controlled using this series voltage injection. We can make the maximum power transfer before 90 degree, even at more 90 degree, because artificially we are creating 90 degree using this series voltage injection. So voltage control, series impedance compensation, phase shifting. But if we add it at any angles, then we can take all these three features or any all combination of them. So this is actually the beauty of UPFC, and we have learned in this lab actually to a small version of that, how it can be implemented. That's all. If you have any question, you may ask me. Otherwise, you submit the report within the next week, as I have suggested. Do you have any question? Shayan Banerjee, how long were you in the meeting? Shayan Banerjee. Only write in your chat box, in the chat box, and go. That is the thing. Supratik Ghoshal is there. Pratik Kumar Mishra is there. Saurabh Barman is there. So they are not present in the lab class. I do not know. I shall check it later whether they have written in the chat box. They are Saurabh Barman. They have written at 10:05 their attendance, but they are not continuously present in the lab. Okay, I shall report this one. I should report this. Okay, I am repeating these names again. Supratik Ghoshal, Abir Chatterjee, Pratik Kumar Mishra, Saurabh Barman. These students were not. Yes.
Abhi Chatterjee, present, ma'am.
How long were you present in the lab?
From the beginning.
But when I have, I have,
I was having some technical problems with my voice, with my microphone. That is why I couldn't respond.
but you have not written in chat also, I think.
I have written my name, ma'am.
Now after that, when I have called the name by later, then you have not responded anything. You are not present in the lab, I think, because you have not written anything in the chat even. It is also your responsibility to attend the class properly. When if you are present in the lab, then every recording is there. From there, it can be identified that whether you are present in the lab or not. Okay. Anyway, thank you very much.